Okay.
Then start.
All right.
Already.
Right. So, hi everyone. My name is Pieter van Houben. I'm from the University of Antwerp in Belgium, and I'm here to present to you my research that I have done in modeling mass flows in HVAC systems using a cycle-based approach. So maybe a little bit of context. My background is I'm a mathematician, so I have not a lot of background in BIM and construction and all, but I have been involved in the project to work mainly on the models that lie behind the energy, calculating the energy and the workings of the system. Now, to frame a bit why, oh, no, it doesn't work. Oh, yeah, it worked just. Yeah, okay. So the project that I'm a part of is about using reinforcement learning agents or model predictive control agents to control HVAC systems. So we do that because 15 to 30% of HVAC energy use is wasted due to faults on the first and improper controls on the other hand. If you have great components that work very efficiently, but you don't control them right, then your system is still not efficient. Then, so as I said, we use reinforcement learning is a AI technique where you allow a model to train itself by interacting with a system and then finding a reward from the system. Now, in case of an HVAC plant, this reward can be the energy use. It can also be the comfort of the people in the building. But of course, you don't want to use an untrained reinforcement learning agent to start controlling a building like this, because then it would probably start experimenting, heating up rooms to 30 degrees or more, cooling them in winter, which is not useful. It would get really bad rewards. It would learn, and then after a year or two, it would know what to do. But those years would be very uncomfortable. So that is why we want to train these agents first in a simulated environment. But of course, if you want to train them in the simulated environment, then the simulated environment must mimic the actual behavior very well, because otherwise the agent will learn a policy that doesn't match the actual system. So that is why the framing of my research in simulating HVAC systems is mainly on how an HVAC system will react to control actions. So to that end, an HVAC system, how it interacts with the building, we can look at it in three phases. First of all, you have the thermal interaction between the components and the building, which is simply a conduction model, thermal conduction. Then there is the calculation of the mass flows in the system and applying those mass flows to the temperatures. Now, why is this so important? Because when a heating source is warming water in your system and you need heat in a radiator, it takes a while before the hot water reaches a radiator. So it's important to model this in your model. And this presentation handles a technique to efficiently calculate this delay between the water that starts from a place in the system, for example, the heat source, and the radiator. But a little spoiler, I am not using this technique anymore because in the months since January when I submitted this paper, I found a better solution to this problem. But I think the technique that I used here could be interesting, so that is why I'm still presenting it here. But if you want to know more about what I'm actually doing now, feel free to ask. So first of all, before we get to the advection part where we shift the water through the system, I'll first have to introduce a little bit on how we do the thermal interaction. So very simple. Let's say this is a pipe. We divide it into a few volumes, and we assume that those volumes have a uniform temperature. And then we solve the heat equation as an interaction between those volumes. This gives us a system of equations, and we solve it using an implicit Euler scheme. Now, I'm not going to go any further in that, but it's important that you know that the components in the system are all divided into volumes of water. Okay, then the next part is the mass flows. So first I'm going here. So let's say we have a very simple system. We have a heat source, 2 radiators in parallel. Well, then calculating the mass flows comes down to looking at each section between those dots there, what the mass flow is, because we assume that the water in the system is incompressible, meaning that the mass flow in this part will be the same. Mass flow in this part will everywhere be the same. So we just need to calculate what are the mass flows in each of those sections. Now for this research, because we are not focusing on pressure equations here, we just want to apply these mass flows to the system. We use a simple demand-based approach to calculate the mass flows. More specific, what we did was, let's say we have this radiator here, then we assumed there was a certain demand flow to have the heat necessary to heat the room. And we assume that the system will provide this flow. And for this radiator, the same. And then we simply calculated the mass flows by summing these flows for these radiators over all parts of the cycle that these are part of. So if you look at this section here, this will need to provide the flow for both radiators, meaning we need to sum those mass flows. Now, this was the first thing when you are simulating buildings from a demand perspective and not from a hydraulic perspective, and this is a really nice technique you can use because it is fully parallelizable over the different cycles in the system, and then you simply need to sum those effects. Okay, so now we have the thermal interaction, we have the mass flows in the system. By the way, I didn't highlight the third cycle there with the bypass, but that's also present, of course. So now the next question is, how are we going to shift the temperatures according to those mass flows? Because of course, as I said, all components are divided into volumes. These volumes all have different temperatures, but now we need to shift those temperatures according to the mass flows to simulate the delay in the system. So very short, if we have a pipe, that's what I show here, and you have a time step delta t, then the fluid will shift an amount of m dot delta t over one time step. What we do is we have these volumes shift, and then we will mix those volumes back into the fixed volumes. That is the operation that we are working with. Now, that is not a very difficult operation, but the problem is if you implement this in a simple way, then the calculation will take very long. And as said in the beginning, we want to train reinforcement learning agents. They need to train a lot with the system. So if each time step takes half an hour to calculate, that won't be very efficient and you won't be able to use your reinforcement learning agent. So what we did is the following. As said, we divided the system into cycles. And we did this to solve the first problem, which makes shifting the water through the system hard, namely the splits and the mergers. Because you have to keep track of where the fluid is splitting into different pipes and where it is merging. And what we did was we looked at all the cycles, and then we simply shift the water through each cycle separately, and then again add all the effects back into the system, the same way as we did with the mass flows in the beginning. So that way, all the splits and mergers are automatically correctly calculated. But then the last challenge was the following, namely, if we take a cycle, let's say this is one of the cycles that I just showed, then the volumes in that cycle will all be of different size because the pipes are divided into different volumes, the radiator has a different volume, so it's an irregular volume field. What we do is it's very simple, we shift the water through this field and then we mix the volumes back into those fixed volumes where they end up. But that is a very costly operation each time step because if you need to calculate for each volume how much of it ends up in which volume, and that all, doing it every time step for a different mass flow becomes very costly. So Now we come to the technique that I use in this paper. What I did was, instead of calculating this shift directly on the irregular field, I created the same field with the same total volume and divided it simply into regular volumes. Now, the difference is that in this cycle, for example, this volume is the radiator. These two are a pipe that goes to the radiator. This is the heating source. In this field, the volumes don't have any meaning. It's just the total volume divided into volumes of equal size. But the main advantage is, if you want to shift the water through this regular volume field, then you only need to do one calculation, because if you shift this volume, let's say we shifted 40% forward, then 40% of this volume will end up in this one. But of course, because all the volumes have the same size, that holds for all the volumes in that field. So you only need to do one calculation instead of calculating it for all of these volumes. Yeah. So what the thing is, it's of course not a free meal, because you still have to do the transformation from the irregular field to the regular field, shift it, and then do the transformation back. So the transformation is the overhead of this method. And so in conclusion, what we saw, we compared this method in terms of simulation speed on different setups of buildings with 4 rooms, 14 rooms, and 100 rooms. Each room had then 2 radiators to see what the scalability was. And what we saw was that when we use very coarse volume field, meaning only 1 volume per pipe, 1 volume per radiator, we saw that the irregular field was still the dominant method, because you have to do a lot of calculations, but only on a few volumes, so the transformation is a dominant calculation there. But then when we did it on a finer grid, so when we use a lot of volumes per pipe, then we saw that this transformation was the dominant method, so it took less time. Then finally, we also compared the irregular volume fields to a method where we parallelized over all cycles. And we saw that this parallelization, again, was only useful when you use a very fine volume field, because in a coarse volume field, the parallelization overhead became again dominant over the gain from the parallelization. And then I have one of the graphs. This is one graph. The other graphs are all in my paper. And what you see here is the simulation times for the method. These numbers here are the number of volumes that I took here in the regular volume field. As you can see, and as is expected, more volumes is a finer grid. Takes a longer time to simulate, and eventually it becomes slower than the irregular methods, which are the 2 at the end. Now, this was for a coarse volume field, and as I said, the irregular methods were still better. In my paper, you can see the graphs for the fine grid, and there you can see that these methods until about 250 volumes were faster than the exact methods. So that was it. Thank you for listening, and if you have any questions, feel free.
This seems a very, at least for me, from an engineering background, it's if I want to know the key messages that could help, would you give some key messages for people from engineering side to make use of the method that you developed?
Yeah, well, the key message here is that